the 360 on Energy and Carbon podcast, hosted by 360 Energy. On today's podcast episode, we have two guests from Geosource to discuss what Geo-Exchange is and how to implement it. First, we have Michael DeWeerd. As project engineer at Geosource, Michael is a technical leader and is proficient throughout the Geo-Exchange design and construction process, from building energy modeling to the detailed design, construction, implementation, and operation of a ground heat exchanger. As an alumnus from the University of Waterloo, Michael brings strong competencies in geological engineering principles and a diverse background of experience, including the design and construction of deep foundation and ground improvement elements, civil engineering consulting, and production line optimization. Next, we have Darren Hagan. She works as a development manager. Much of Darren's work at Geosource has focused on technical and financial modeling of Geo-Exchange projects and assessing value of Geo-Exchange systems from a variety of stakeholder perspectives. With a degree in environmental engineering from the University of Waterloo, Darren has a strong understanding of the technical side of the energy space, but combines that with a passion for knowledge translation and relationship building. Throughout thoughtful communication and content development, Darren works to break down silos in the industry and facilitate candid discussion with the goal of collaboratively establishing an equitable and sustainable post-carbon future. Now let's get into the episode. Welcome back, Dave and John. We have some new guests joining us today. Welcome, Mike and Darren from Geosource. We are excited to have you. Mike and Darren, are you able to give us a bit of your career background and what you do at Geosource? Darren, I can start with you.
Absolutely. Thanks so much, Lysandra. It's a pleasure to be here. My background is in environmental engineering. I've known since I was about 10 years old that I wanted to pursue a career in the sustainability space. It's literally genuinely all I ever wanted to do. So when the opportunity to work at Geosource came up about a year ago, I jumped at the chance. So in my role here at Geosource, I'm a development manager. So on the technical side, I support our engineering teams through the preliminary stages of the project through, technical and financial modeling of the geothermal systems. So I support a lot of our clients in understanding the value of the geothermal system on their particular project. And so, I help pass them along, from business development through to, the final engineering team. I have a strong passion for communications and education. So I've been supporting the more business development and marketing side as well through rolling out some more comprehensive education programs to support industry writ large on how Geo-Exchange is working and how it's growing and all of that fun stuff.
Thanks for that, Darren. We're really excited to hear about the background of Geosource too as we get into it. Mike, how about you? Could you give us a career background and what you do at Geosource?
Yeah, so I've been with Geosource for about 3.5 years now. I started out primarily working with the construction arm of the business, which at the time, that was the only arm that actually existed. So I got to spend a good amount of time on site, getting my hands on our systems and building them, which in my opinion was the best and quickest way to learn the ins and outs on how these things work. So it gave me a real practical connection with the construction of geothermal heat exchangers. But fast forward to now, I'm the project engineer at Geosource, which means I'm heavily involved with all things technical, so all things design. I still have plenty of involvement with the construction side of the business, but most of my time is spent working in our engineering and development department. So from early stage feasibility level to detailed design to the implementation of our systems and then finally the operation of our systems.
Yeah, between the two of you, I think we're going to get some really great answers on these next few questions. So I'm going to pass it off to John and Dave for those heavy-hitting questions now.
Okay, thank you for that. I don't think mine's a heavy-hitting question. My question's really a bit of a scene-setter question. I'm familiar with geothermal, geo-exchange and terms like that, but we have quite a wide audience who might not exactly know what that terminology means. So my question, if you like, is a starter question. What is geo-exchange? And how does it work?
For sure. It's a great question to start with. We get questions like that a lot as well. Ultimately, Geo-Exchange is a heating and cooling system that operates by moving heat between the ground and whatever needs to be heated or cooled. Most commonly, it's a building as Geo-Exchange is used very often in HVAC solutions. It's commonly referred to as geothermal energy as well, but that can get a little confusing just because there are other kinds of geothermal energy that typically rely on extracting high temperature fluids from deep underground. And that's, when it's used for power production, we see a lot of that in Iceland, Hawaii, Australia, New Zealand, places like that. The Geo-Exchange in and of itself is a different kind of geothermal energy. We're just leveraging the consistent ambient temperature of the ground as a heat source in the winter and a heat sink in the summer. And the main reason why Geo-Exchange is considered so efficient is because the ground, about 10 meters below the surface, is the same temperature year round. The actual temperature can depend on where you're located geographically, but we typically see temperature ranges in and around 10 to 12 degrees Celsius in Southern Ontario. So ultimately, when it's 40 degrees Celsius in the middle of August, instead of your air conditioner or cooling tower trying to release more heat outside, your Geo-Exchange system can reject heat a lot more efficiently. That is, consume less electricity to cool your building to the exact same set point. So in the winter, instead of combusting fossil fuels for heat, you can extract heat from the ground. So when this is compared to other electric forms of heating, like air source heat pumps or electric resistance, Geo-Exchange is a lot more efficient because, when it's the middle of winter, it's negative 30 degrees outside. Geo-Exchange systems are connected, to a much more comfortable 10-degree resource, which is the ground. And ultimately, because Geo-Exchange is reliant on that consistent ground temperature, it's important to maintain balance in the ground, to maintain that operational efficiency. So in order to keep that temperature consistent, we need to make sure that we are moving heat back and forth between the ground and the building in a balanced way. So that would be, taking out the same amount of heat in the winter that you're putting back in the summer. So, with our more modern data acquisition and building automation systems, this can be pretty simple. So it's not overly complicated in that way.
Thank you for that. It is, I suppose, certainly here in the UK, what the technology you're talking about is sometimes referred to as ground source heat pumps. But I must admit, I rather like the terminology Geo-Exchange because it makes it a little more approachable and a little more interesting, doesn't it, by having that sort of title?
Absolutely. I'd say it's quite visual. I think, the actual exchange component is typically a big piece that's missing for a lot of people. They just think geothermal, we must be extracting heat, but it's a two-way exchange. So I think that word is very helpful.
Yeah, I think one of the things with we were talking, is this emerging technology? Well, no and yes. But I think one of the things with all of these things is we've really got to work on the language, haven't we, if we want more people to understand what we're doing.
100%.
Darren and Mike, I just want to echo, because prior to this session, we were talking about geothermal versus Geo-Exchange. And truthfully, I certainly didn't understand the difference. So you've enlightened us already on that. The other thing, as a business guy, when I hear Geo-Exchange, that gets my interest. It sounds like a financial transaction. So all of a sudden I get more interested in the topic right away. So anyhow, I'm just sharing you as a business person how that might capture people's attention. My question to you is, why would someone want to transition to a Geo-Exchange system from what they currently have in place or considering down the road?
Well, I'd say that there's, obviously there's a number of benefits. I think starting with the most practical is that, Geo-Exchange in and of itself is a net zero ready technology. We don't burn fossil fuels and it's inherently high efficiency. So it fits within that net zero space that I think everyone is relatively well familiar at this point. We kind of see ourselves moving towards it. So, just putting a Geo-Exchange system isn't, magically going to make your building net zero. But as far as the HVAC system itself goes, it's net zero, unlike anything else that would consume or combust fossil fuels. And I think, if we accept the fact that we're moving towards a more electrified sort of system, comparing itself to other forms of electric heating and cooling, Geo-Exchange is highly efficient, meaning it consumes less electricity, and it consumes less electricity, I think, in particular in peak events. And that would be, in an HVAC perspective, the hottest day of the year, the coldest day of the year, which I think is really important as, in Ontario, regionally specifically, our electricity grid is summer peaking, meaning that we are purchasing power production for the hottest day of the year. And so with Geo-Exchange, we're tied to that 10 degrees Celsius, nice, cool, nice, ready to go ground temperature, so that in the middle of the summer, we're consuming less electricity in that really critical time. So we might be able to save ourselves some trouble, collectively, in terms of, having to buy more solar power, more wind power, more nuclear, more forms of power. So it can help lighten the load there as well.
Yeah, so you just described not only a benefit to the end use customer, but you've also a benefit to the grid. So I just follow up on that one. So I understand it's a lower demand if this was implemented. In the winter, would the demand of power for these systems be similar to the summer, or is there any change in the electrical usage based on different seasons?
I think it would largely depend on the performance of the buildings. As we move towards higher efficiency buildings, we're going to need less heating energy requirements just because they're built to be well insulated. And so it's likely that we would still consume, more electricity than we are now, obviously, because we're using fossil fuels more heavily to heat our homes. But we would still be consuming, I would say, probably less electricity than we are in the summer. I don't have a crystal ball, unfortunately, but I can see that with climate change progressing, we're likely going to have hotter summers. And so that's going to even further increase the amount of electricity required in the summer.
Well, it's good. That's really good. I thank you for sharing.
I don't want to be negative, but years of being in the engineering profession, I have seen, shall we say, misapplication of technology, which sometimes happens. So my question really is, what are the challenges, or what are the aspects that might prevent somebody from successfully implementing a Geo-Exchange project?
So a few things that can come to mind, just to name them off, things like space constraints, drilling conditions, and the major one being cost. So thinking about space, so on a small scale residential system, they might opt for a horizontal geothermal or geo-exchange system. So horizontal systems are cheaper than vertical systems. But the drawback is this requires a larger surface area. So the solution for them here, if space was limited, would simply go with a vertical system. Primarily what we install, so by drilling vertically. And if you consider large-scale systems, which is, let's say, our bread and butter, more of what we do, such as high-rises in the urban setting, it's only really feasible for us to consider vertical systems. In an urban setting, it's also common for a proposed high-rise to be constructed from basically property line to property line, or at least very close to it. So this leaves nearly no adjacent space to the building to install geothermal boreholes. So on nearly all developments then, we actually place the vertical boreholes beneath the building, which solves that issue. But as developments are getting taller, their footprints do not necessarily get larger. So you can understand that a taller building may require more heating and cooling capacity, but must be installed within the same footprint. It's not a common occurrence that we run out of room beneath a building, but the solution to this is drill deeper or utilize angled boreholes if this is technically possible on the site, or to then finally decide to potentially hybridize the system with auxiliary systems where geo makes up a majority of the heating cooling requirement, but it's supported by in-building mechanical systems. And then there are retrofits. So this is probably our most common candidate for projects with space issues. An existing building that's getting, say, a facelift or being upgraded to today's building standards or greater. The building's already standing, so we are limited to drilling from any available space around that building. So in any high-rise or mid-rise retrofit project that's in an urban setting, it's highly likely that the amount of space required for a typical vertical system isn't possible. So this led to us developing the ability to drill angled boreholes. So angles from vertical up to 20 degrees or so. So these boreholes they're still more vertical than not. 20 degrees is not much. And so yeah, don't think horizontal directional drilling angled, but still primarily vertical. And this allowed us to drill, say, from one side of an existing building and flare out the boreholes at various angles and directions towards the opposite property line. So in some cases, using this, we reduced the amount of surface area required by up to 95% with this method, making previously impossible retrofits possible. And just as a reference, So typically, if we're doing our typical deep borehole, we might require 20-foot spacing at surface if you're doing vertical holes, 20-foot spacing between any adjacent vertical hole. When we do these angled holes, we've gotten fairly precise with it with our GPS systems and inclinometers that we actually can start these holes as little as a half meter apart, so a foot and a half, and shoot them off at the various angles. So that's been a big development in the technology that's allowed us to take advantage of these retrofits. If the building is standing, it's still not a lost cause in an urban setting. We can still deal with that.
Okay, could I have a follow-up question on that?
Yeah.
And it's a cheeky one, perhaps, but we're talking about, area we need for horizontal and boreholes. Could you put some kind of scale on this? What kind of area, what kind of depths of borehole we're typically talking about?
Yeah, so our typical day at work, we're doing 850-foot boreholes, so 850
Right.
feet deep. Previously, we were commonly doing 600s, but we quickly realized that we need more capacity in the ground, so we need larger pipe, we need deeper holes, and yeah, we're actually probably not going to stop there. At some point, we're going to have to consider going deeper. So
If you hit
850
oil,
today. Well, that's actually funny because the next thing I want to talk about is the drilling conditions, because we're going deep enough that we do find natural gas.
right.
Right. Okay.
And
So
yeah, that's going to be interesting if you do. Yeah. Carry on. Sorry.
Yeah, no problem. So yeah, we're drilling pretty deep. Our typical system is, as I said, about 850 feet is our average borehole length. And at some point, we probably will have to go deeper. And we do hit natural gas in southern Ontario, which, I mean, it sounds concerning, but it's typically very low pressure, low volume pockets that vent in a very short amount of time. But there are areas, however, that may not be eligible for us to do these deeper holes due to higher pressure, larger gas containing strata. So in these scenarios, we may just be required to install a larger quantity of shorter boreholes, just so we don't get into that mess of that zone. If let's say gas was commonly known to be 500 feet in an area, maybe we'll drill to 400 or 350. Just have a large margin of safety there.
Well, thank you for that. That is interesting.
Another one of the challenging factors can be cost. So why might Geo be worth it in the first place? Well, there's typically an increased initial capital cost to install these systems, but then there's a reduction of operating costs. So this means that there's going to be a payback of X number of years, or there's going to be an internal rate of return of Y, whatever factor you may use. So on a small scale, say for an individual home, the homeowner needs to be willing to make that upfront investment and then trust that there will be reduced operating expenses. So the homeowner may find that the payback period is too long if they also decided to build a highly thermally efficient envelope of a home. I mean, if you think about it, a better envelope will require less load on the HVAC. Less load on the HVAC means less avoided costs, and less avoided costs means even slower payback if you're to go the Geo route. So making the investment in other performance enhancing areas could reduce the appeal of them going Geo. If their goal isn't primarily financial based and they're just trying to make the most efficient home possible, then Geo's always the way to go. But yeah, so on a larger scale though, say for a high rise, a developer will see the increased price tag to install the geothermal as opposed to the conventional system. If the development is a proposed apartment building, the developer, or say a sister company of the developer, will retain ownership of that building for the foreseeable future. They're going to rent those units. In that case, they'll look at the increased capital cost to install this system, and then they're going to have to factor in the reduced operating costs and see if that internal rate of return indicates a worthy investment, or whatever factors they prefer, which we often see as well worth it. But the challenge is, if the development says it's not an apartment building, but it's a future condominium, where the ownership of each unit is transferred to a new buyer, this changes things. Since the developer is going to be hands off the building once it's complete, they will never actually see the benefit of the reduced operating costs to generate a return on that capital investment into the ground heat exchanger. So the condo owners will actually see that benefit. So from like a cost and investment perspective, it's not wise for them to install a ground heat exchanger. But I mean, we hope other factors could be at play, such as, I mean, company green initiatives or more stringent building code standards. But like if you consider it from just the quality of the developer's investment, it would probably be a poor choice. And then to solve this issue, this is what led us to offering our ground heat exchangers as utility assets. So we design the system, build the system as we normally would, but we don't sell the system to the developer in this case. The system will be owned by a joint venture between ourselves and our development partner. So there's actually no direct cost to the developer to incorporate Geo in this case. Plus, they benefit from reducing the need to install the conventional systems that they would have had to install anyways. So it's a win-win for the developer, and our joint venture gets to make the investment in the technology.
And it's a clever model. It's sort of like the hot water heater that we all rent versus own. And that overcomes the issue that you just described. Because what we find, and this won't be a surprise to you guys, is that most organizations don't really understand energy cost or life cycle cost. So that's a challenge we all face in trying to get people to look at more efficiency. But I do understand in the construction industry, you've got different people that are driven different ways, and you've come up with a solution that actually can overcome that. So good on you guys.
Yeah, thank you. And then on that life cycle cost piece, I mean, we can convince people left and right with our spreadsheets of the life cycle cost is X, but they have to believe it, and that's the hard thing. So in the case where we take it as utility, we know the technology so well and we believe in it that we trust the numbers. We don't have to convince ourselves. So it's much easier to convince ourselves to make that investment than others.
And I would say as well that utility offering, it kind of helps one of the other main issues that we're seeing and just, the general, I would say, scariness of doing something different. Largely, we've built buildings and heated our buildings a very certain way for a long time. And switching the way we do that is also one of the big barriers to getting Geo in the ground. And so having an energy expert like Geosource and our partner OEC to stay behind and take care of the asset, that can help, reduce some of the fear, I think, associated with doing something different when there's no pressure there.
Darren and Mike, we have listeners from around the world. It's not just Ontario based. So a question for you guys is, what would make a building an ideal candidate for Geo-Exchange? Could you provide us what your thoughts are on that?
Yeah, from a technical perspective, I mean, we can make geothermal work with nearly any building. It depends on what your primary goal is. Is it to offset carbon emissions or reduce total energy use? In the market today, what we usually see as the largest driver on what makes a building an ideal candidate is just the economics of the system. So what's the return on the investment? All the other factors, the emissions and the energy use, they luckily just come with it regardless. So factors that affect capital cost of the system or factors that affect the avoided operating costs, or savings is another way to think of it, can push the needle in either direction for what would be considered a better system. So some of the key factors there that can affect cost would be geology. So geology can be a major factor here, as the geology beneath the building will directly affect the cost of drilling. And it can even affect the size of the system when you consider, say, the thermal properties of the geology in that particular site, because it varies as you move around. So it's a common misconception that we drill until we find bedrock and stop there. In the GTA or Greater Toronto area, we're drilling through bedrock, and it's actually more cost effective than drilling through the overburden soil. So in short, deeper bedrock is almost always more expensive here. If we were talking like very hard igneous or metamorphic bedrock, the opposite can be true. In the Greater Toronto area, we have relatively soft shale and limestone, which is it's great for drilling and it has great thermal performance. And performance mainly referring to like the thermal performance of the envelope of the building. So higher performing buildings are typically better candidates for geothermal or Geo-Exchange than lower performing buildings. Not by a huge margin by any means. All of them are easily eligible, but we just control the systems differently, and they have different benefits. The higher performing buildings here will require an increase in cooling load and a decrease in heating load when compared to its lower performing equivalent. From the ground heat exchanger's perspective, that leaves us with more heat being sent to the ground than we're extracting from the ground. As Darren was talking about before, we need to bring the system into thermal balance. That means we must remove heat from the system on an annual basis to keep it in balance. So finding uses for heat is easy. Start with your building's domestic hot water, then tack on snow melt in wintertime, pool heating if you have it. And adding some of these new heating loads to the system can even reduce the required system size because it brings it into a more thermally balanced state. And we have this exact scenario on a very high performing building we are in the design stages for in Etobicoke right now. Like these guys will be taking advantage of like very efficient domestic hot water heating just as a consequence of building a high performing envelope. We almost have to twist their arm to do domestic hot water. It's almost a requirement just to keep it into balance. But I mean, they're not complaining by any means.
So I just want to pick up, like, just to make sure I got this. Is there specific geology that is ideal for this? I know I heard you say that you can go anywhere. For our listeners, is there any specific geology that would be best suited for this technology, cost effectiveness, stuff of that nature for the work you guys do?
Yeah, there's a good amount of variables there. Best is probably cheapest from a drilling perspective. So the thermal benefit from going from overburdened soil to like a very high thermal conductivity igneous bedrock like granite is probably not worth the extra cost in drilling. So best case scenario, you're drilling through sedimentary bedrock, shales, limestones, carbonates, stuff like that are near surface. So shallow overburden soil and then sedimentary bedrock is what we see as the most cost effective systems.
If we looked at Canada, is there any particular regions specifically that you think would be ideal target areas in Canada itself?
So I'm very familiar with the geology in our area. So we do a very high concentration of projects in the GTA. If you go in the Oakville, Burlington area, you can't beat it. It's bedrock in 10 to 20 feet, and it's relatively soft shale and limestone that have good thermal properties, so it's just perfect. You can't really get any better than that. As you go north, we start hitting the hard stuff. We start hitting granite and gneiss and all those types of things, which we still drill through it. It's more expensive. It takes more effort.
Okay.
This brings me to our next question. How can our listeners optimally implement a Geo-Exchange system in their next project? So for instance, a lot of our listeners come from the greenhouse industry, manufacturing, automotive, etc. How do they get started with even considering a Geo-Exchange system at their company?
Yeah, that's a really good question. And I think the answer is very clear for us. It's keep Geo-Exchange in mind on day one and make sure that everybody knows it. Make sure the architect knows it, make sure that the structural engineers know it, and especially make sure that the mechanical engineers know it. It's very easy to implement Geo-Exchange with developments, but like any system in a building, a holistic approach where all systems are considered in unison, the best outcome can be achieved. So what can happen is, as the Geo-Exchange design builder, we can arrive at the table very late in the design stages because geothermal or Geo-Exchange was an afterthought. Maybe the development's already at like a permit level drawing set. The architect probably has not accounted for, say, the basement level mechanical space required. The mechanical engineers may have already made heat pump selections and circulation pump selections and sized pipes with certain fluid temperature expectations that just don't jive well with Geo-Exchange. For the building now to properly adapt to a full Geo-Exchange solution, major overhaul in the mechanical consultant's work could be required. An architect may have looked at what mechanical has done. Maybe they looked at their heat pump selections, say a 2-ton unit for a single bedroom unit, and ensured it fits in that unit. The architect's not going to be happy if mechanical now says, oh, we need a 2.5 ton. That no longer fits in the allotted space. Or maybe it's instead decided not to rework the previous work by mechanical and to instead hybridize the system to be, say, supported by natural gas when Geo-Exchange can't supply the temperatures they assumed from day one. So a proposed low emission development can all of a sudden become a natural gas hog in this scenario. So yeah, so I think you can see how a late decision to consider Geo-Exchange can trigger a daisy chain of rework. So consider it early and everyone will benefit from it.
Could I come in with an additional question? With Geo-Exchange technology, does this present any unique long-term maintenance issues?
So it's a very low maintenance technology. I mean, we build our closed loop systems with high density polyethylene plastic. There's reports that try to characterize the life expectancy of high density polyethylene plastic that's been built properly. And they say greater than 100 years, or they say 100 years, because I mean, we don't really know. Plastic is plastic. If it's built properly and you don't dig into it, the stuff's going to last. So the actual Geo-Exchange portion of it, our ground heat exchanger, is extremely low maintenance. Then if you look at the building side of your system, the building side of your system probably did not change. It's going to be what it would have been regardless. Maybe you made different heat pump selections. Maybe you made different equipment selections overall, but that side of the system is going to be the same, or actually probably less maintenance, because you're going to operate the system at most likely a lower temperature set point if you had say a central solution. So there's no new maintenance scares other than your fluid should be your heat exchange fluid should be looked after. You want to maintain antifreeze concentration if you have it. You want to just ensure there's corrosion that is not happening, just like you would in any closed loop mechanical system. And you want to swap, say, inline fluid filters on a regular basis. So it's all basic stuff. But when you look at the ground heat exchanger itself, if built properly, the thing is it's going to outlive probably all of us.
Mike, it's something that hasn't been addressed, but I know in our exposure with working with Mohawk College, and they've got a net zero building, they've conveyed that the value of going this route actually reduces their machine room size dramatically, which is attractive for them versus using the standard boiler and other HVAC equipment. Do you find that's a point that's discussed or addressed with customers, and they see that as a favorable point to go with the heat pump?
Yeah, that's a big selling point, especially if you're talking to architects. They love this. If you can remove rooftop mechanical from a development, that's a massive value add. You're making it easier for structural. First of all, you're giving the potential for adding an extra floor of suites, because they typically build these things right to the limit of what their site plan approvals will allow them to. Instead of having a rooftop mechanical, maybe they can put everything in the basement parking garage, which we do, and now they can sell that much more real estate. So they're all over this. They love it.
And I think to build on some of the points that Mike had made as well, not only can we reduce the footprint of mechanical rooms, but the equipment in the mechanical room typically has a longer life cycle because of some of the things that Mike had mentioned. We're dealing with lower temperatures typically than conventional systems. We're not boiling water. It's more ambient. So your pumps and the pipes on the building side are also likely going to last longer, and the maintenance cycle on those are likely longer, maybe in 25 to 30 years instead of 15 to 20 years of the conventional systems as well.
Well, this leads me to our last question. What is the biggest takeaway you can give our listeners from this episode? So if we're talking generally about Geo-Exchange, what it is, how it's implemented, what's the biggest key take that we discussed from this episode?
Geo-Exchange technology is not new. As you guys hinted to before, you've seen it before. It's just becoming mainstream now, and it really does work. There's no rare combination of factors that will make a development or a project eligible for the technology. It's robust. It can nearly work with anything if you have the right team at the design table. Developers remove Geo-Exchange from consideration due to discomfort with the technology, because they fear making a major change in their typical basis of design. But what we have seen time and time again is that the developers that make that jump typically implement Geo as a standard for new developments.
And so I think ultimately, your listeners is to keep Geo in mind. And I think it's important to be open to changing the way we do things. Reach out if you know somebody who's implemented Geo, ask them questions, reach out to us at Geosource. There's a number of other specialist in this space. And so I think it's important to be open to that change and open to communications about this, and ultimately having the courage to get over that hump, so to say, and do something a little different, because it'll ultimately pay off. We promise.
Well, thanks again, Darren and Mike, for joining us today. Dave and John, any final comments?
I'm very glad you touched on the point about lower temperatures, because one of the problems we've seen in the UK with people trying to apply this technology is using it, but trying to use it with a conventional heating system, which obviously operates at a higher temperature. But I think you spread out the case, so to speak, for Geo-Exchange very well there. And it should be something with, how can I put it? If it's done well, and I think you've touched on this a few times, if it's done well, it should be one of the go-to solutions.
Yeah, I'm going to echo John. I actually think this is going to become a standard going forward because of the net zero requirements and the speed. So it's proven technology. I think people are not aware of it. We're hopeful this type of podcast educates people so they become more aware and understand it. And I appreciate the stuff that you've covered, because I think that will help people with that. So thank you, Mike and Darren, for sharing your knowledge on this. Really appreciate it.
Yeah,
No
thank
problem.
you.
Thanks for having us.
That's all for today's episode of the 360 on Energy and Carbon podcast. Thanks for listening. Make sure to check us out on our website at 360energy.net and follow us on LinkedIn at 360 Energy Inc. Tune into our podcast on Apple Music and Spotify by searching the 360 on Energy and Carbon. You can watch the video recording and subscribe on YouTube at 360 Energy Inc. See you next week.